Yeah, I want to thank you all for coming to our second lecture of Phyllis and George Halburn radio astronomy seminars that we've been organizing in the last few years. This quarterly seminar series is supported financially by the Halburn family and also by the department chair, who is basically supporting the videotape of this series. Videotape and audio tape of all the talks that we've had so far can be found on this website in case you miss some of the talks. So today we're actually pretty happy to have Eric Wilcots from the University of Wisconsin, Madison. He went to Princeton to get his undergraduate degree and then went to University of Washington and got his degree, I think in 1992.
Yes.
His thesis was about star formation in the Magellanic Clouds. And then he got a fellowship from National Radio Astronomy Observatory. It's a Jansky, prestigious Jansky fellowship, and he went to Socorro in New Mexico. And he was there for 3 years, and he shifted, I think, his interest towards studying basically gas content of galaxies. And essentially that's where all the baryons are. And today he's going to tell us about basically the studies that he's been doing in the last several years or so. But before I finish, I want to also mention that Eric is also a dean. He was originally an associate dean, but now he moved up the ladder in the last 10 years or so. He's a deputy dean of the College of Science and Arts.
Letters and Sciences.
Letters and Sciences. Okay, that's how they have a different name for it than here. And so he's managing to do everything, and he's still moving up in the administration sort of ladder. So today he's going to talk about searching for missing baryons and the cosmic wave at the radio wavelengths. Before I finish, I want to mention also that we have pizza at the end of the seminar. Please stay around. Okay.
Great, thank you.
Yep.
Thank you. It's great to be here. I had some great conversations this morning already. Looking forward to some more this afternoon, and so thank you for inviting me to come up. And I know you've had these radio astronomy lecture series, and just a little bit of a tidbit that Karl Jansky, who my fellowship was named after, now the VLA is a Karl Jansky Very Large Array, is actually a graduate of the University of Wisconsin. And what I just learned recently in the last few months or so was that his older brother was, for his PhD at Wisconsin, developed a transmitter. And the first broadcast of public radio occurred in Madison from Chamberlain Hall, where our physics department is, by the elder of the two Jansky brothers. And so Wisconsin and radio astronomy and radio go hand in hand. So I want to talk about something a little bit different from what you might normally associate with radio astronomy. And that is really the search for and probing of gas that is outside of galaxies. And this is not something that radio astronomers have typically done. It has largely been the purview of our colleagues who use the optical and the UV part of the spectrum. But I want to get into that a little bit and talk about how we might use and how we are using radio telescopes to probe this very important component of the universe. So the overview, a very brief overview, is I'll talk a little bit about what we know and what we don't know about the gas outside of galaxies. And it's going to come in two different bins that I will use. And one is the so-called intergalactic medium, which is really the gas in between galaxies. But later on in the talk, I will also refer to something called the circumgalactic medium, which is the gas in relatively immediate environment of individual galaxies. We'll talk about what we know about the baryonic content of galaxy groups. And I focus on galaxy groups because that is the most common environment in which to find galaxies. Most galaxies live in relatively loose associations that we call galaxy groups. It's very hard to get a quantitative definition of a galaxy group. It's one of these things that when you see one, you call it a galaxy group without being able to define it very well. But it's really important for galaxy evolution, and I'll talk a little bit about that. And then I'll talk about the new traces for finding this stuff. So we'll start with a very simple slide coming from our colleagues from WMAP, giving the overall census of stuff in the universe. And what you'll immediately recognize is the baryons up here comprise something like 4 to 5% of the stuff in the universe. I will not be talking about any of this other stuff of what the universe is mostly made out of. And so what astronomers do is we're trying to play around with and understanding the evolution of that baryonic content. And I'm going to get into that in some more detail as we go along. So if we try to do a census of the baryons, and this comes from work done some time ago by Fujita and Hogan and others have done similar compilations of the baryonic content of the universe. We start with the obvious stuff, and that's stars and stellar remnants. Right? Relatively easy to trace, but really doesn't amount to much. Okay? 0.4% of the critical density, about 10% of the baryons are in this form. Okay? Stuff that we can easily detect. We can then might turn to something of favorite of radio astronomers, and that's cold atomic and molecular gas, probed by radio telescopes, and that's even less important in terms of the critical density, less important in terms of the total baryonic content. And then we think, well, maybe a bunch of this stuff is in hot X-ray emitting gas that's typically found in clusters of galaxies. And you can see here that maybe about 5% of the baryons or so. And then there's an intergalactic plasma, and back in the late 90s, and I'll talk more about this, that's where people thought that maybe most of the baryons were hanging out, in part because groups were so numerous. Right, and that there's so many of them, and we may be able to probe this stuff. And there are always some ideas about something more exotic, and most of those have been ruled out as different exotic ways of finding the baryons. But even if you do all the tallying here and you add up all the numbers, what you find out is on this list, something like half of the baryons that should be there are not in one of these easily identifiable categories. And so there is essentially a problem in extragalactic astronomy of missing baryons. We're very confident that they should be there, both from a combination of looking at the cosmic microwave background and ripples in that, also the implications from Big Bang nucleosynthesis. Both of those give us a really good prediction of how many baryons should exist in the universe, particularly now at redshift of 0. If we do this relative simple accounting, we're missing a bunch of them. Right? And so one of the things that I'm focusing on is, are there ways that we haven't tried of trying to track this stuff down and see where these missing baryons might actually be? Okay, so we'll start again a little bit with the intergalactic medium. And this is material that was long thought to exist. This is one of the compelling slides that came out of the early releases from Sloan, showing you what is known as the Gunn-Peterson trough. The way this data is acquired is by pointing at a very distant quasar. In this case, the object is at a redshift of 6. It's a very high redshift object, taking the absorption line spectrum of it. And what you'll notice is that this is the Lyman alpha line, and the emission in the rest frame that is shortward of Lyman alpha, so very strong UV radiation, is completely absorbed. And that absorption comes from a fairly dense neutral intergalactic medium along the line of sight to this particular object at a redshift of 6. Right? And so by probing out very distant in the universe, we're seeing that at a very high redshift, the universe is very neutral, lots of gas in what we will call the intergalactic medium. Since that time, the universe has become highly ionized. And one of the big areas in extragalactic astronomy these days is understanding when and how that reionization took place. But still fundamentally we're seeing in this data that there exists at very high redshift a fairly dense intergalactic medium that likely contains most of the baryons at high redshift. And so one of the things we're trying to understand is how do we evolve from this situation at very high redshift to where we are today. So if you do a simulation, this might be the view of the universe that you get. There's a number of these simulations. Some of them are very, very powerful these days as we've gotten better computational capacity. This is the dark matter distribution as a function of redshift of 3, 2, 1. This is the universe now as we see it. We take that dark matter, put it in a gas density. Okay, you see a similar thing. and this is the temperature of that gas, where red is fairly hot. So this is essentially looking at a galaxy cluster with a lot of hot gas, and then this is the metallicity of that gas, which tells us something about feedback from massive stars. Right? And we can see how that evolves, at least in the simulation, over time. What I want to point out, in the early 2000s, Dave and other collaborators looked at simulations very similar to this and reached the conclusion that many of the baryons, maybe as much as 30 or 40% of the baryons, might actually be in this filamentary network, the so-called cosmic web, and not so much in individual galaxies. Right? And so even in the early 2000s, they say, folks were thinking that this web comprises many of the baryons, a temperature of 10 to the 5 to 10 to the 7 degrees, probably not that hot, probably closer to the 10 to the 5 than the 10 to the 7. More recently, others doing some UV spectroscopy have really brought that number down to about 15%. Okay, so 15% of the baryons may be in this cosmic web of material. It gets us closer to fully accounting for the baryons, but still leaves us in a place where we are missing some. All right, and so to give a sort of a close-up of what this cosmic web might look like and how it connects to individual galaxies, this is the sort of the cartoon. This comes from a simulation, I shouldn't say cartoon, of what we might expect to see how individual galaxies, particularly those in the field that is outside of clusters, might interact with this cosmic web. And this gives us a sense of how to trace the matter in the universe. So the red here is the cosmic web itself. Relatively warm, maybe 10 to the 5 degrees. Okay? The yellowish green is going to be metallicity. So that is essentially gas that's probably been thrown out of the galaxy due to supernova feedback or some other type of feedback. The dark blue is cold gas that sort of weaves its way through the cosmic web. And one of the things for those that work on galaxy formation and the early evolution of galaxy, right now most people would say that galaxies get their gas through something called cold accretion. That is the idea that there are these cold filaments of gas that somehow feed from the cosmic web onto a galaxy. And that's what we're seeing here in this simulation. Right? There has yet to be an observation where I think we can confidently point to and say, yes, that is cold accretion happening, and that's what it looks like. Right?
You might define for some other people what cold and warm.
So cold here is going to be of the order of 1,000 degrees. Okay. So this gas should largely be neutral. We think the cosmic web, the red stuff here, is about 10 to the 5 degrees. That is what we're going to call warm. If you get up to sort of 10 to the 6, 10 to the 7, we'll refer to that as hot. Okay. So the idea is that this is a fairly warm distribution of baryons that the galaxy is residing in. How does gas go from that phase of being warm to being in a cooler phase? And to make stars, we need gas down at 100 degrees. How do we get that gas from the warm phase into the cold phase inside a galaxy where it can make stars? Okay, this is a challenging problem. For a long time, people thought maybe the warm gas sort of condensed out, and there are models essentially of rain, that you would get condensation from this warm gas onto the galaxy. But now most people are going with these simulations where there are these cold filaments that can exist within that warmer gas. And we should see the direct accretion of cold gas onto galaxies. As I said, we have yet to have an observation of a galaxy and say, yes, that is cold accretion. Okay? One of the things that we're trying to do.
These two different phases are in pressure equilibrium.
They must be in similar pressure equilibrium, yes. Okay, so here's another way of looking at this, and I tell people, and I oversimplify what a galaxy does. And from an extragalactic point of view, and for those of you that hold the Milky Way near and dear, and all the intricacies of the Milky Way near and dear, forgive me for a moment, galaxies are simply designed to convert gas into stars. That's what galaxies do. Okay? Lots of other interesting things happen, thank you. But I will say that galaxies convert gas into stars. And the question that I and my collaborators like to go after is, how is it that galaxies acquire their gas? And what role does the environment play in that process? Right? And so this is a sort of a model from Lilly and collaborators of how this might work. The galaxy is right in here, in this container. There's some long-lived stars that are buried here. There's star formation that happens. There's a gas reservoir, so gas comes into the galaxy, gets converted. Sometimes it gets converted into long-lived stars. In other cases, it's returned back, perhaps in an outflow, which could dump gas into a larger halo, which we'll talk about a little bit later on, or completely out of the galaxy. We can get gas inflow from external to the galaxy and gas inflow from into the halo that sometimes doesn't make it into the galaxy. So it's this fairly complicated mechanism of getting gas into the halo, the immediate environment of the galaxy, getting that gas into the galaxy where it can form stars, thinking a bit about that feedback from making those stars, what impact that might have on the supply of gas, and then thinking about how it is all connected to a larger environment. Okay, and I've defined this, I've introduced this term, the IGM, which is the intergalactic medium, and the CGM, which is the circumgalactic medium, and I'll talk more about that in a second. Okay, so the way that this gas in the halo around a galaxy, in the circumgalactic medium around the galaxy, has historically been probed, has been using absorption lines, particularly in the ultraviolet part of the spectrum. Okay, and this is where, similar to work Dave did for many years on the ISM and in the Milky Way, looking at optical spectroscopy. Most of these are looking for tracers which are primarily in the UV. This is a particular one, magnesium-2, showing up at a wavelength of about 2800 angstroms. And the idea is if I have enough background sources, I can take a spectrum of the background sources, I can measure the absorption caused by magnesium-2 along the line of sight, and see where that is relative to a host galaxy. And the idea here behind this plot is that the equivalent width, that is how much magnesium-2 there is, as a function of distance from the galaxy, here in the units of the virial radius of that galaxy. And what you find with all these plots, and these are various different samples, etc., is that when you get fairly far out in the galaxy, you're getting lots of upper limits, okay, but there is some magnesium-2 that seems to hang about outside of the optical extent of the galaxy. So probing the so-called circumgalactic medium, that there is magnesium-2 absorption. You can then go through some various calculations about how ionized is that stuff, what the abundance is, and lead you to a conclusion of how much neutral gas there might be. Okay? And that's a conclusion that folks like to try to reach. But we do have evidence of this. And then if you do the calculation to convert it into a neutral content, so neutral hydrogen in the column density, again, as a function of distance from the galaxy, there's one virial radius. These observations, the magnesium-2 line, again, going through the corrections of ionization and abundance, lead to a conclusion that even very far out, 1 to 2 virial radii, we should expect to see a low column density of neutral hydrogen gas that's associated with the galaxy. Okay, that's an effort to probe the circumgalactic medium. Okay? And again, this work is largely done in the UV part of the spectrum. And so the picture that you can form based on this is that a galaxy like our own Milky Way, right, where there's the large Magellanic Cloud and the small Magellanic Cloud, is embedded in this distribution of gas that is the so-called circumgalactic medium. Okay? And this is what a galaxy looks like. All right, again, largely coming from looking at ultraviolet spectroscopy. Okay? Another example, and this is one that my current grad student did, actually as an undergraduate at Colorado. This is just a random galaxy here, but coincidentally on this little bit of the sky they had 3 different quasars, 3 different background sources to which to do spectroscopy. And getting the measurements here discovered that at a distance of 65 kiloparsecs, which is really far, well beyond, this is about 2 virial radii of this galaxy, there should be neutral hydrogen with a column density of 10 to the 15 or so, existing that far out from the galaxy. So this picture of a galaxy embedded in a much larger distribution of gas is very consistent with the UV spectroscopy that people have done for the better part of 2 decades. Okay. The interesting thing is that if you take all of this and to its logical conclusion about how much gas there might be in the so-called circumgalactic medium, you get that the mass of the CGM is comparable to the gas mass of the galaxy, and even beyond that. And that there are some who would say that in a mass budget of a galaxy, the cool circumgalactic medium and the warm, hot circumgalactic medium, so this would be at 10 to the 5, this would be at 10 to the 3 to 10 to the 4 degrees, actually amounts to more mass than that's inside the galaxy. So that most of the mass associated with an individual galaxy actually resides in the circumgalactic medium and not in the galaxy itself. Okay? So that's where, for an individual galaxy, the bulk of the baryons exist beyond the optical extent of the galaxy, in a phase that is, at least up until recently, best traced by using UV spectroscopy and looking at absorption lines in the UV part of the spectrum because of the temperature and the conditions of that gas. Okay?
So what's the ratio of the stellar content to the gas?
Usually the stellar content is the disk mass here is all the stuff in the disk. And so for these galaxies, it'll be the stellar mass is probably maybe 50-60% of the total disk mass. Okay, and so here's another picture. This comes from Philip Richter, thinking about the Milky Way and the local group. So we've got the Milky Way here, Andromeda M31 over there. The pinkish stuff is the circumgalactic medium in which those galaxies reside. And then his point here was what we're lucky to be able to do is have a number of sight lines to other quasars that help us probe the local circumgalactic medium. And so this is work that is currently going on. Okay. So now I want to move a little bit away from thinking about an individual galaxy to thinking about the larger environment in which galaxies reside. And these are so-called galaxy groups. The Milky Way resides in something that we very poetically call the local group. A colleague of mine calls it the local misnomer, with the notion being that from afar, if you go far enough away, the local group looks like two galaxies. It's like the M31 in the Milky Way. So is that really a group, right? Or are we just calling it a group because we're inside of it, right? But groups are very interesting. And here's an idea. This is from a simulation, the illustrious simulation work I did with a summer student, Kelly Sanderson, former grad student Kelly Hess, and one of our current students, Alicia Kundert at Wisconsin. This is just going to the illustrious simulation, which is one of these new simulations of the universe, of what a galaxy might look like in stars, or a galaxy group might look like in stars, and then looking at the gas content of that galaxy group, where over here we're looking at sort of the mass in individual cells in the simulation. And so you can see that the green, which is the relatively high mass stuff, the higher mass pixels are associated with individual galaxies, but the group itself is buried in this low density, again, circumgalactic medium. In this case, it extends across the entire group. Okay? What I'm very interested in doing is sort of probing this blue stuff, because that's where most of the baryons are going to be. And how do we probe that gas? And the reason for that is that this blue stuff, this gas here, probably has some effect on the gas in the individual galaxies, okay? And again, it's where most of the baryons are. Right? So that's what I want to go after.
So what is it limiting the size of this cloud?
That's going to be just the gravitational potential of the group.
So it's
that's just essentially the virial radius of the group itself. Okay, so here's something that might seem unrelated. Okay, I'm going to walk through this diagram because for extragalactic astronomers, it's a really fun diagram, but there's a lot to unpack here. One of the great things from the Sloan Digital Sky Survey has been finally the ability to look at large samples of galaxies and try to understand them in a statistical way. And that's what this plot does. What we are plotting here is what we call the color, comparing the intensity of the galaxy in two different bands, U, which is close to ultraviolet, and the red, and the absolute magnitude or the luminosity of the galaxy here. We will take luminosity as a proxy for mass, okay? So that the most luminous galaxies are also the most massive galaxies. We'll take the color here, and astronomers being, we love to characterize things. And so what you find here as you go to the upper part of this diagram, things are so-called red, And so very cleverly, the grayscale here just shows a lot of galaxies fall up here in the red part of this diagram, spanning quite a bit of range in luminosity, and that has gotten the name of the red sequence. Down here, a little more diffuse distribution of galaxies. These are relatively blue, because we're at smaller numbers here. This is the so-called blue cloud. Okay. And then astronomers said, there's a few galaxies in between, and we'll call that the green valley. Okay. This is basically just saying color versus luminosity. Right. There's a lot buried in color versus luminosity, or color versus mass. As I said, we'll take luminosity as a mass. And the idea being that a galaxy on the blue cloud ultimately ends up on the red sequence. Right? Because I said, galaxies are converting gas into stars. Blue galaxies are star forming. So those are galaxies that are still forming stars at a relatively healthy rate. So they appear to be blue. But galaxies eventually lose their ability to form stars. And one of the jargon terms in extragalactic astronomy these days is something called quenching. And that is how do galaxies stop forming stars? What causes that end of star formation in a galaxy? What causes a galaxy to be quenched? Or, different way, what causes a galaxy to move from the blue cloud onto the red sequence? And there are a number of different ideas that go along with this. The blue crosses that you see on this diagram are all of the galaxies that have been detected in neutral hydrogen. Okay? And so this is the spin-flip transition of neutral hydrogen that leads to a transition at 21 centimeters. It is the spectral line for centimeter wavelength astronomers. Right? We like our H1 line. Because it probes that most important of the elements. Probes are neutral hydrogen. And so this comes from work done by Alfalfa, which is a survey that was carried out by the Arecibo telescope to just look at galaxies in the nearby universe. And what we find is that the blue cloud galaxies tend to still have neutral hydrogen, that gas out of which stars eventually form, whereas we see many fewer galaxies in the red sequence that still have gas. And so the takeaway here is that quenching, that evolution of galaxies from forming stars to no longer forming stars, is a question of what happens to the gas content of galaxies. And that's where radio astronomers come in, because we get to measure the gas content of galaxies and their environments. Okay? It turns out that much of this transformation, this transition from being a blue cloud galaxy to being a red sequence galaxy, probably happens in galaxy groups, because that's where most of the galaxies are. Okay? And so this transformation, we think, is going to happen in galaxy groups. And so there's a couple of things that I want to highlight, a couple in the yellow, that are two of the processes that we think are driving this transition of galaxies from blue to red, the so-called quenching of galaxies. We're answering this question of how do galaxies get rid of their gas and shut down star formation. Okay? There are a number of ways. Interactions can do it. Active galactic nuclei can do it in some way. We're still working on that. But a couple of ones here is ram pressure stripping. If I take a galaxy that has some gas and I allow it to move through an environment, through an intergalactic medium that is relatively dense, I can calculate what the ram pressure is on that galaxy caused by its motion through a dense medium. Right? And we do see some examples in galaxy clusters where that ram pressure is sufficient to strip the gas off of the galaxy. So a galaxy can lose its gas because it's moving through a relatively dense environment. Okay? We do see that in some galaxy clusters. So it's ram pressure stripping via an intergalactic medium acting on the galaxy. The second one is more subtle, and it has the unfortunate names of either strangulation or starvation. Right? And if you remember back a few slides, I showed you that sort of picture of what the galaxy looks like. You've got a galaxy embedded in this very large circumgalactic medium. What if I get rid of that circumgalactic medium? The galaxy has some supply of gas in the disk already. It's forming stars from that. So it will work its way through the gas that it already has. But if I've gotten rid of the circumgalactic medium, it can no longer refuel. And so what we'll see is a gradual shutting down of star formation driven by the loss of the circumgalactic medium. We call that strangulation or starvation. Okay? So two different processes, both of which require the interaction of the galaxy with a gaseous environment, a larger scale gaseous environment. Right? And that's where the work that we're doing comes in. Okay, so we talked a little bit about UV spectroscopy. Here's some work I did a few years ago with my first graduate student, just looking at a random background source through a galaxy group. Don't worry about the name, but it was a long way from the nearest galaxy. Right? And we got some UV spectra, and sure enough, there's absorption lines here, particularly oxygen 6, little Lyman alpha. And from all of that, we concluded that the density of the intergalactic medium must be about 10 to the minus 4. Along this sight line through a galaxy group, but not near any galaxy. So probing that blue gas that we saw in the simulation. Okay? But I admit to a certain level of frustration that the number of sight lines in the ultraviolet part of the spectrum is small. There just aren't that many of them because there just aren't that many bright enough UV sources, and our UV telescopes aren't big enough. And just one sight line through a galaxy group is very unsatisfying. Right? So I thought, well, are there other ways that we can probe the gas inside a galaxy group? Yeah, hop in. Yeah. That was the individual cloud that we thought we were probing there. Yep. And so other folks have gone on and look at galaxy groups, and here is the conclusion from a recent paper by Sanderson and collaborators looking at a number of galaxy groups. And I'll get back to this in a moment. But I just want to point out something else, is that they have tried to account for all of the gas in hot gas, 10 to the 6, 10 to the 7 degree gas, and stars, and they're falling way short of what the baryon fraction should be. Okay, so even when we look at galaxy groups, when we count up the hot gas, we count up the stars, we're missing some baryons. Okay, some of those baryons might be in that gas that we're probing with the UV spectroscopy. This is just a compilation of those results. That is what we should be expecting, and we're just missing a lot of the gas, the baryons. Okay, and so my motivation is to say, okay, let me use a radio telescope to see if I can attack this problem. Because I'm a radio astronomer. And so this is an image of the Very Large Array, still currently the best radio telescope in the world, 27, 25 meter dishes in New Mexico. Fantastic instrument. And this is one that I've been using for the duration of my career. So our first guess was, let's go look for neutral hydrogen gas in galaxy groups. That's where the baryons are. We just got to get a big enough picture. We'll go find some neutral hydrogen. We'll count it all up. And this will all work. So here's an image of a galaxy group, an optical image. The contours there are what you get when you look at the 21 centimeter line of neutral hydrogen. Yes, there's lots of hydrogen. Okay, but it's typically associated with individual galaxies. Sometimes there's a tidal bridge between two galaxies. Sometimes they're very extended, galaxies merging together. It's all great astrophysics to understand the H1 content, but it does not amount to the total baryonic content of galaxy groups. Right? There is neutral hydrogen gas. It's very interesting, but it doesn't get us to where we want to be in accounting for all the baryons. We did similar work looking at Arecibo, and what we've done here is just taken lots of galaxy groups. We've got about 700. We bin them in different bins. These are your small groups, 4 to 5 members, 6 to 9 members, 10 to 19, and then more than 20, and just stack them on top of one another. So we took the centers of each group in this bin, stacked them up. The things with blue diamonds have H1 gas. The thing with black crosses do not. And what we do see is that as the galaxy groups go from being very small to being much larger, is that the nature of the neutral hydrogen content of the group changes. The concentration of those galaxies that have neutral gas changes. Their distribution, they're much more widely distributed in the larger groups than they are in the smaller groups, and the fraction of galaxies that hang on to H1 in the larger groups goes way down. Right. Yeah?
So is this the number of these groups. Is that sort of a proxy for halo mass? Is that the idea?
Yes. Yeah. We use the number of galaxies as a proxy of the mass of the group, right? Because for many of these, we cannot independently measure the mass. We can try, but not independently. Okay. So we did this and came up with the conclusions, as I just mentioned, that there are fewer H1 sources in large groups. The H1 sources are less concentrated than the galaxies that don't have H1. Low mass galaxies in the groups, and I didn't point that out on the previous plot, seem to lose their gas earlier. That is, the percentage of low mass galaxies without H1 is fairly high, even in the smallest groups, and it's really high in the large groups. So low mass galaxies tend to lose their gas in lower mass galaxy groups. Okay? And if you remember from the previous couple of slides that the processes by which galaxies lose their gas, we think dependent upon an interaction with an intergalactic medium. And the results that we see by stacking the H1 content of groups across a wide range of masses seems to be consistent with that. Right? That there's something happening, particularly in the larger groups, that deprives galaxies of their cool gas. Okay. And so thinking about this, and a conversation I had with Ron Eakers when I was on sabbatical in Australia. And I was talking to Ron about radio galaxies. And he mentioned to me a paper that he wrote in 1978 looking at what were then called head-tail sources. These are in the early days of interferometry, even before the VLA was built. So this is actually using Westerbork data, that Ron had discovered a couple of these head-tail sources, which I now will call bent double sources, that resided in galaxy groups, or what he called poor clusters. And this was strange, because radio astronomers had discovered double-lobed radio sources dating back to the 60s. The fact that some of them were curved, such as in this image, which is taken from Blanton et al., and this is one of our sources. You can see there's the center of the radio galaxy, the jet there, coming back, it's curved. The fact that some of these were curved was a bit of an oddity. The conclusion was, based on early statistics, is that the bent radio jets all resided in galaxy clusters. And the bending of the jet was a result of ram pressure, of the radio galaxy moving through the dense intergalactic medium of a cluster. Clusters have very high velocity dispersions, so the velocity of the source is probably 1,000 to 1,500 kilometers per second, moving through a relatively dense medium. You can go through the pressure calculation and say, yeah, that might work. We might be able to bend the jets of a radio galaxy as long as it is moving with a high enough velocity through a dense enough intergalactic medium. And we see that in galaxy clusters because they're very massive and the velocity dispersions are very large. What was interesting about Ron's result was that these two bent doubles were in galaxy groups where the velocity dispersions were more like 300 to 400 kilometers per second, and there was no evidence of a dense intergalactic medium. There was no X-ray emission. There was no independent evidence that there was actually something for this radio galaxy to be interacting with, but yet the jet was bent. And so, to me, I said, that is the way we can probe the intergalactic medium of galaxy groups, is by looking for bent doubles. Yeah?
Does this jet get out of this small galaxy going through the...
Oh, yeah, there's the galaxy itself. Oh, yeah, the galaxy's there. Right, so the jet is well extended beyond the extent of the galaxy.
So it's like tens of kiloparsecs?
Yes. And so we set out on a project with Gretchen and Emily Freeland, and this project's been continuing ever since, to look at bent doubles in galaxy groups. And so we went through the first survey, which is an all-sky survey, or most of the sky done with a VLA, fairly high resolution at 20 centimeters, so 1.4 gigahertz. As of now, at least for the northern hemisphere, it's still the best survey for the radio sky. It's fairly sensitive. We selected about 30 bent doubles from that, ones that were not in clusters, so that were in low-density environments, okay, to be able to probe galaxy groups. And so the first phase of this is to use radio continuum observations to measure the curvature of the jet and the jet power. I'll talk about that in a second. And the second phase, which we're deep in the middle of now, is to look very deep to see if we can see evidence of trailing synchrotron emission from these bent doubles, and to really probe, maybe getting to your question, where the bending takes place, right, to be able to understand that. But we'll get to that.
So I'm sorry, why aren't you actually observing in H1?
Because the jet is not emitting in H1. The jet is a.
You're looking into the environment.
Looking into the.
going through.
I am looking at the effect of the environment on the jet. Let me get to my next couple slides, and maybe that will. Here's just a couple of images of some of our sources, and here's an example of the type of work that we do. We find a radio jet. Right? We measure the radius of curvature. There's the galaxy itself. So yes, this jet is extending well beyond the galaxy. It is in an environment. We try to get some optical spectroscopy to get a velocity distribution of the environment in which the galaxy resides, to try to get at least an estimate of its velocity relative to its environment. And from that, we put together an estimate of the density of the intergalactic medium. And it's really based on this work, which ultimately comes from Euler's equation. It is the idea that if I can measure the radius of curvature of the jet, if I measure the jet thickness, so H and R, if I have some idea of the velocity of the galaxy as it's moving through its environment, right? And this comes from looking at that velocity distribution. The radio continuum gives me an estimate of this, since of the jet momentum. So this is from the observations of the radio continuum intensity, the curvature, the thickness of the jet, optical spectroscopy of the environment, and then I can derive a density of the intergalactic medium, okay, assuming that jet is being bent by Ram pressure. And so the reason we use radio continuum is we need that radio continuum to actually be able to see what this jet is looking like. And we could do this for a number of sources. There's a couple of examples, and we get densities of, in some cases, 10 to the minus 3, in other cases closer to 10 to the minus 4. This is a very interesting object because this is the only one for which we have really deep Chandra data, and there is no X-ray emission. So this is not a hot intergalactic medium that this galaxy is moving through. Right? We are not detecting it in X-rays.
How do we know the density of the jet and the velocity of the jet?
We know the jet power, and we are simply making some assumptions about the jet velocity and its density. Yeah, we do not have independent measures of what that jet density are. Right? We can use, so what we actually did in this paper is use sort of an average value for jets from other observations to assume that was in there. So it's one of the things that we don't know. We would love to be able to get better data on that.
You see a relation between the velocity of the galaxy, so the direction of the velocity of the galaxy, and the direction of the bend?
No. All we see is that whenever we see a bent double, it is not at the center of the group. So if we make some sort of geometric center of what that galaxy group might be, the ones that are bent doubles are not residing at the center, which would be unusual if they were. It'd be hard to imagine how it gets bent if it's sitting at the center. But there's no correlation between the direction of bending and the redshift of the galaxy. Okay, so we've done this now for a few, and I'll just show you one example. If we extrapolate the density that we are getting in the intergalactic medium, and say, okay, let's assume that there's a halo, and fit that halo to the measurement that we get for the density of the derive from the bent double, and say, all right, how many baryons are in this thing? This particular thing, we actually get more baryons than we really need. And so we think by using the bent doubles in these environments, we are detecting the presence of the baryons that are missing. And it's very likely that they're not missing, they're just not at a temperature and a density that makes them for easily observed in emission. It's probably closer to about 10 to the 5 degrees. Really hard stuff to probe observationally. Right? So we do think the galaxy groups might be hanging on to a large fraction of baryons as we're detecting by the bent doubles. And our work was followed by really interesting work by Louise Edwards and collaborators, who just stumbled across the bent double, and it's not bent a lot. There it is, their geometry of it, sitting in a filament. So there's a galaxy cluster and there's a filament, one of that bits of the cosmic web, feeding into this galaxy cluster. Their object is sitting here on that filament. It's a bent double. And what they conclude is that the density of the intergalactic gas inside that filament, inside that bit of the cosmic web, is about 3 times 10 to the 5. Right? So even outside of a structure, inside one of those filaments, we are seeing evidence of gas. you're seeing evidence of where the baryons are. Okay, as probed by looking at the bending of radio jets in radio galaxies. One of the implications of all of this is, if we think about it, and this is just a plot that we put together showing the velocity of a galaxy, the density of the intergalactic medium, and for various different masses of neutral hydrogen gas, under what conditions would that gas be stripped out? Okay, getting back to this question of what quenches the galaxies. And what we do find, not surprisingly, is that for the densities that we're measuring of the gassing groups, there are galaxies that are holding on to 10 to the 6, 10 to the 7 solar masses of H1, that under a wide range of conditions, velocities and densities, those galaxies would likely lose their H1. Hence leading to the quenching of that converting from a blue galaxy to a red galaxy. Okay, and the other thing, if this worked, it worked before. So with my colleague Sebastian Heinz and his postdoc Brian Morsoni put together a simulation of the bending of a jet. This is basically just setting off a jet in a simulation and having a wind blow by it that is comparable to the ram pressure we would expect for the galaxy group. And what you see there is you do see the bending of the jet, so this is what we are observing. But the interesting thing about this is he's also predicting that we should see a very diffuse sort of trail of synchrotron-emitting gas beyond or behind the bent double. So the bent double will be moving in that direction, and we should see this trail of very faint gas. So I'd love to be able to stand before you and say, yes, we have detected that, but I can't because we are beating down signal to noise. So we have a project with the VLA to look at this stuff really, really deep and to try to tease out this faint emission. And we're not at the sensitivities that we need yet, but we're trying to get there. To see if we can find this stuff. Okay, we're also doing an experiment to look with the VLBA, very long baseline array, because it's much higher resolution, to try to understand where that bending takes place, because that will give us a sense of sort of what's going on. One thing the back of my mind that I worry about in thinking about this is if the bending is happening inside the galaxy, it is not the intergalactic medium. And so in my mind, I really want to know where that bending starts to take place. And so we actually have a program going on right now with the VLBA to try to identify the place where the bending starts. So that's work in progress, and we're working on that. Okay, I want to spend the last couple minutes talking about some other neat way of thinking about the intergalactic medium using radio telescopes. And this gets inspiration from our UV friends. Our UV friends have long taken the approach of finding a sight line to a background source and taking a spectrum of that source and using that to probe the intervening medium. Okay. We can take the same approach in radio astronomy. And one of the powerful ways is using something called Faraday rotation. And this is the notion that if I have a background source that has some angle of polarization, as it moves through that radiation moves through a medium with some density and submagnetic field, the angle of polarization will change. And I can measure the angle of polarization as a function of frequency. Okay? And if I can do that, that's what the Faraday rotation here is, this rotation measure. That will give me a sense of what the product is of this density times the magnetic field. So A, it tells me that there is an intervening medium, and very interestingly, it tells me that it's magnetized, right? That I have magnetic fields in the intergalactic medium. The notion of being able to do this is made easier if I have enough background sources. Right? And so here's sort of a cartoon of the idea. We're also doing this with some distant intermediate redshift galaxies. You've got some background source. We're sitting here in the Milky Way. We look at the Faraday rotation of that source. We do it without a galaxy intervening. We do it with the galaxy intervening and see if there's a difference. The challenge, of course, is I'm looking through this Milky Way, which has its own interstellar plasma that causes problems. The foreground is, Dave, can we get rid of that? Can we please get rid of it? So this is a problem. And this is a problem not only for the work that I want to do, but also for our colleagues who are probing the microwave background. They are dealing with the foreground of the Milky Way in droves. Right? It's a problem because we're looking through this stuff. The best way we can do this is try to do it statistically, and since I'm running out of time, I'll just sort of jump to this is very recent work that we're doing with Anna Williams, my current graduate student, looking at a nearby galaxy group. It's a large angular extent on the sky, about a degree on each side. And so we've got about 30 sources, radio sources, that we're looking at through the galaxy group. Right? And the idea is to see, can we detect a rotation measure signal arising from the intergalactic medium that then be sitting in this galaxy group? Right? And we love to have more sources to do this. Those are our pointings with the VLA. We get a lot of polarized sources, which is great because we need polarized sources. So that's all good. The results, yeah. Wish I could come and tell you, yes, we nailed it, we found it, right? But that's not the way it's going to work. So what we've done is taken our background sources that are within the virial radius of the group, so out to a radius of 420 kiloparsecs from the center of the group, compared to those outside the virial radius of the group. Right? And so what we're looking at here is the rotation measure. Just the number of sources, and that's the rotation measure. And the one thing that is interesting about this distribution, okay, other than it looks like there's no fundamental obvious difference between the rotation measures measured against objects outside the virial radius compared to those inside the virial radius, there is a difference in the dispersion. That we're seeing a larger dispersion in the RMs for things that are inside the virial radius of the group, right, which might indicate a bit of a turbulent magnetic field. Right? So this is really a demonstration project that we are doing. We think the technique actually works. We think it should be able to lead to really interesting probes of this gas in between galaxies, particularly in groups. The trick to being able to do that, I'll skip through those, is getting lots of sight lines. We're doing this with 30 sources. We would love to have about 100, okay, to build up the statistics. So how do we get 100 sources through a given group? Okay? And that is where I get excited about what's happening next. And this is an image of Meerkat, right, which is the South African radio telescope that is going to be commissioned, I believe, by the end of March, because I believe the Minister of Science and Technology has promised a bonus to everybody working on the project if they get it done by March 31st. So there's an incentive. But Meerkat is an array of 64 dishes in South Africa. It will have much faster survey speed than the Very Large Array, and it will be able to do work like our rotation measure survey. And by going deeper, we will be able to get more sources and to be able to look at these rotation measure grids through local structures in a much more sensitive way. So as I say, Meerkat is coming online. There's an Australia telescope precursor as well, and that hopefully will lead to some really great new discoveries about how we can use radio telescopes to probe the intergalactic medium. So I think I'll stop there and take any questions. Thank you.
Thank you so much. Michael?
So you had several nice examples of event sort of dual jets, and they all petered out after a certain, they kind of spread out.
Yeah.
It's like they're running into something.
Yeah.
Now, doesn't that give you a measure of the density? I mean, the length of the jet and the way it peters out, that must depend on...
That does depend on the density of what it's running into. And we, on a separate project I'm doing with Sebastian, we actually have much more complicated simulations of jets and trying to understand what it's telling us about the density of what it's running into.
Because the simulation you showed was close, but not exactly like the ones
Yeah.
you saw. It's very skinny initially. And
Yep.
suddenly very
That's to be able to simulate what a jet really looks like, and that's challenging. But we are working in that direction. Yep.
Okay.
So the presence of that green valley in that graph you showed there implies some sort of relatively quick time scale for this to occur.
Yeah.
Are you able to put any constraints on that time scale based on the random pressures and velocities that you're observing?
It's tough because the Green Valley, it could be mythology. Okay. In the sense that it's not really a place. And I'll explain it in this way, that if I have a blue galaxy that's star forming, and you're seeing it at a slightly different inclination, so I'm actually dealing with a lot of interstellar extinction, it looks redder than it should. And so it might show up in a green valley. Okay. So there was a paper some of the colleagues in the Sloan survey wrote. I think it's The Green Valley is a Red Herring was the title of the paper. So whether or not that actually is a transition region is a question. But the time scale for quenching is a really good question. And I think the way that we're going at it with some other collaborators is really trying, to our best of our ability, probe the star formation histories of galaxies. So if you can see, boy, star formation was happily going along, and then over some couple 100 million years, 1 billion years, it petered out, that would give us a sense of what's driving it. But the Green Valley, I wouldn't jump into the Green Valley and say, yeah, that's where you want to be.
So if you strip the circumgalactic medium from a galaxy by ramp pressure, where does that gas go? Can it be used to enhance the star formation rate of another galaxy in that cluster?
It probably hangs out in the cluster. It is probably the stuff that we are detecting in by other means. If it ultimately falls onto some other galaxy, yeah, it could do that. But it just hangs out in the intergalactic medium around that cluster.
Because you did show that some of that intergalactic medium will
ultimately, as I say, it could find its way in a group. Maybe it ends up cooling and falling on some other galaxy. We're a long way from being able to trace stripped gas, particularly stripped circumgalactic medium, in an environment. Although there are really neat things at the cluster scale, where you're dealing with higher masses, higher velocities, higher temperatures, with new X-ray technology to begin to actually look at the motion, the dynamics of what folks are calling intercluster weather. Okay? So that's a way, and even with radio telescopes like Meerkat, one of the really neat things, if you can start getting down to low enough surface brightnesses in the synchrotron emission, you can begin to understand how uniform, the answer is probably not very, but how turbulent the intergalactic medium might be by probing the really faint synchrotron emission. So that will be something that I've been looking forward to Meerkat and the other SK precursors being able to do.
I have a question. How do you didn't say much about the magnetic field.
Yeah.
So how does that play out? How does it play out with the gas, and what's the origin, and what do we know?
So so we were hoping with our Faraday rotation experiment to be able, ideally, when I wrote the proposal to the VLA, said we'll be able to constrain the magnetic field in a galaxy group. Right. What we can tell now is it's if we're detecting this increasing dispersion in the RMs, we are detecting a turbulent field in the intergalactic medium. My guess is that is spread by AGN. And so the jets that we are seeing in the bent doubles with other galaxies, that is pulling and putting a magnetic field into the intergalactic medium, probably doing it in a way that leads to a very turbulent field. The limits on the magnetic field for what we have is down in, I think it's about 70 to 90 nanogauss would be the strength of the field in that particular group that we've looked at.
So is it a pressure equilibrium with the gas?
Don't know yet.
Oh,
yeah, I don't. We're not there yet. Give me a couple more years. We'll try to do that.
Good. Yeah. Any more questions? Well, let's thank Eric for an excellent talk. Thank you.